Hello everyone. Thank you for coming to my presentation on a CG model for my thesis. This is also a presentation for the Global Economic Analysis Conference. Please let me take a time to show you my slide. Here we go. My research question is shown in the title. Do light vehicle emission standards promote environmental goals in Australia? I'll first talk about the motivation, then followed by the CGE modeling part and the result explanation. Australia is one of the largest carbon emitters per capita in terms of per person emissions in the world. In fact, the Australian emissions and the USA's emissions per person is very close. The transport sector accounts for more than a quarter of Australia's greenhouse gas emissions. Light vehicles account for the largest share, 16% of Australia's total emissions. Sorry, I think I forgot to share the screen, but now I think it's right. Therefore, the Climate Change Authority of Australia proposed mandatory light vehicle emission standards to reduce the emissions. What is the proposed standards? In the mandatory standards, it will require new cars sold in Australia to meet a 105 grams per kilometer fuel efficiency. That is a huge reduction from the current level 192 grams per kilometer. It is equivalent to the fuel economy standards, which has been used by many countries, reducing from 8.3 liters per 100 kilometers from the current level to 4.5 liters per 100 kilometers. Many countries from EU, US, Japan, and China have implemented this fuel efficiency scheme for more than a decade. The US is the first in the world to legislate the corporate average fuel economy standards. The recent Obama government introduced the greenhouse gas emissions levels. The target for 2025 is 93 grams per kilometer, or equivalent to fuel efficiency target, which is 4.0 liters per 100 kilometers. Among all the countries, EU has the most stringent target, and Australia is the only one, or among one of the few countries that is lag behind in climate change policy design and implementation. What are the benefits of the standard? It is said that the benefit will increase the average cost of a new car by $1,500, but this will be more than offset by fuel savings from the first year and over the lifespan of the vehicle, leaving motorists better off. But there are some problems with this statement. The first question is, if this leaves the motorists better off, will they drive more? Because the effective price of fuel decreases. This was discussed by many economists through a few decades and is captured by the direct rebound. The second question is, even if they have saved fuel in the transport private automobile, what would they do with the saved money? Would they consume more other energy related appliances or services? This is the indirect rebound, and Sorrow, Haley, and Turner have done some work on this field. The light vehicle emission standards, in essence, is an energy efficiency improvement tool in demand-side management. As early as the 19th century, the British economist Jevons have observed in his famous book, written in his famous book, The Core Question. He said it is a confusion of ideas to suppose that the economical use of fuel is equivalent to diminished consumption. The very contrary is the truth. There are three possibilities of an exogenous technology change. If the rebound is smaller than the savings from the technical advancement, then there will be energy savings. If the rebound offsets all the energy savings, there would be no effective change. And if Jevons is true, rebound is extremely large, that more energy is consumed than before, it will be the backfire condition, or called the Jevons paradox. The theoretical foundations of the rebound effect is grounded in the new classical economics theory. When the fuel use in transport decreases, it means the effective price of fuel in transport sector decreased. Then it will induce behavioral change. We can decompose the effect of energy efficiency improvement into two effects: the behavioral effect and the mechanical effect. The mechanical effect is the direct change in fuel use, the savings from engineering advancement, so it's called mechanical effect. The behavioral effect is what we care about, or the rebound effect. It measures how much more people use after the technical change that is linked by the price channel. We further decompose it into output effect, substitution effect, and income effect. We can set up a cost minimization problem for the form and see what happens, how the demand for petrol use increases once there is an exogenous shock on fuel efficiency. The form faces cost minimization problem. Price of input I times the demand of input I demanded by J, sector J, and sum over I. The form faces a Leontief production function that simplifies the behavioral effect. Now we don't have substitution effect. These capital letters are the level changes. When there is introduce a exogenous technical change Aij, the input change would be the output change plus the input change A. and Yj is the output change of the transport sector. It is, if we only look at it in a partial equilibrium model, we can write out the output change as the price elasticity of demand times the price change. The price change is the cost of petrol in transport, or J, times the technical change. Assume that it is the only technical change in this sector. And the break-even condition says Xij is 0. The change of fuel in transport is 0. Implies if we plug equation 2 into 1, set it to 0, the Aij cancels out. If we rearrange it, we get equation 4, which says this elasticity of demand for J is equal to the inverse of the cost share of petrol in transport. If the elasticity is greater than the right-hand side of equation 4, there will be a backfire condition. Otherwise, energy would be saved or not effective change. There are some problems with the partial equilibrium. It can only capture the direct rebound or within sector rebound, which is usually small because usually the elasticity parameter is between 0.5 to 1, whereas the inverse of cost share is greater than 1. So this small elasticity means the rebound is unlikely to offset the mechanical effect. But we know that the partial equilibrium neglects the income effect and the interaction between industries. So we go to introduce the general equilibrium, taking into account the income effect and the industrial interactions. So we can estimate the indirect and economy-wide rebound effects. We also need to know that if the technical change is small, the results from the general equilibrium modeling would not differ much from that found in the partial equilibrium. Now we can put the general equilibrium to work, put the scenarios into the general equilibrium model. First, we want to see what happens to the business as usual scenario without any policy intervention. We have to determine the level of technical change in the business as usual scenario. This was done by the econometrics. Collect the data from 1970s to 2015, the time series data for average fuel efficiency, and forecast the 2025 level of fuel efficiency, which is 7.3 kilometers per liter. Note that this figure is different from the new car fuel efficiency, but this is an average of all car efficiency from age 1 to age 20. And in Australia, the average age of cars are 10. So this figure is actually around the same new car fuel efficiency level, but in 10 years lag. We decompose the business usual scenario into two scenarios. The first one is a technical change in the industrial sector. which is 1.6 minus change. The second scenario is a household petrol demand taste shift. It means now households use 1.6% less petrol to meet the same amount of utility. The experimental environment is the Orani-G model for Australia, a multi-sectoral comparative static CGE model with 35 industries and 37 commodities. Three primary factors: optimizing behavior of agents, zero pure profit, and market clearing conditions. All these scenarios were run in long-run closure with adjustable capital stocks and fixed employment. This table shows the results for the two BAU simulations. The first column is the industrial technology shock or improvement. It has a positive impact on the real GDP as expected, so it's on the household consumption. The intermediate input change of petrol in transport is minus 1.32. Remember, our shock is minus 1.6. The difference between these two figures gives the direct behavioral effect, 0.28%. If we use this figure divided by 1.6, we get the direct rebound, which is 17.5%, meaning that 17.5% of the energy savings were ruined by the direct rebound. If we look at the third row, output change of petrol, which is minus 0.33%, and we compare it with general mechanical effect calculated down the table, minus 0.72%, which is the technical change 1.6 times the 45% is the proportion of fuel use in transport. For 45% of the petrol is used in transport. This figure between the difference of mechanical effect and the output change gives the indirect rebound, which is 54.2%. The second column shows the result for the household taste change. The demand shock has a negative effect on the GDP and real household consumption. But we have to note that the utility level actually increases because the consumption let down by petrol does not mean that the household is worse off. If we look at the household petrol consumption, which is very close to 1.6, difference point 0.04, indicating the rebound is very small, around 3%. Similarly, we can calculate the household indirect rebound. Now we want to simulate the mandatory standard in the CGE model. I treat these standards as a combination of BAU scenarios with a larger magnitude of shocks, or 7.4 kilometers per liter average fuel use. And the change is 3%. There's no cost imposed on this policy because I treat this equilibrium shift as a pre-play claim by an arbitrator in the corporate game between the producer and the consumer. So before the shock, before the the government or PM announced this a policy scheme, producers and the consumer are staying at a inefficient equilibrium, and they have no intention to switch because the myopic behavior in both sides. When the government announces an what they want to apply, actually we add a stage in the game. We let another one, an arbitrator, announce something that is credible, then both will switch to another equilibrium, which is more efficient. And in the new equilibrium, we assume that consumers are better off. But they won't choose that if nobody tells them to do so. In the new scenario, we find that GDP growth and real consumption decreases, but as before, the utility increases. And output change of petrol decreases by 1.36. The mechanical effect is 3% times the proportion of petrol used in the household and in transport sector, which is quite large, around 80%. This gives a quite large rebound effect, and this is the indirect rebound is around 41.9%. The last two rows calculate the direct rebound from the intermediate industrial change and the household sector, which is small, and the household rebound is similarly small. What do we learn from these rebounds? Under the business as usual scenario, we found the industrial shock or technology change induces more rebound than the household shock. In the policy scenario, we are combining the industrial shock and the household shock with the larger tech change and the larger demand change. This means this induces a small direct rebound but still high indirect rebound. The rebound effect can be as large as 41.9%. It can offset as much as 41.9% of the technical gains in energy savings in the policy scenario. What I'm going to do next will be the carbon emissions account, link this with the result I got, and calculate what happens to the overall economy's carbon emissions. And next, calculate the vehicle compositional change to give a more detailed scenario prediction forecast. Third is to use dynamic modeling, incorporating the economic and population growth. Thank you for your listening.